Hello everyone, welcome to today's webinar which is on physical design. I am Amit Mishra from INVECAS. Today your host would be Srikanth, who is Director of Physical Design at INVECAS. Please wait for a moment, meanwhile he will join and take us to this topic. Thank you.
Hello everyone, good afternoon. I am Srikanth, host of this webinar on design timing closure methodologies by considering the process variations. In today's session, we are going to talk about various sources and classification of the process variations which will have a direct impact on the performance and power of a transistor. Over the period of time, the resolutions, we are going to talk about those particular methodologies and their advantages and disadvantages. At the end, we are going to talk about a couple of comparison results between these particular methodologies. Just to start with the conventional way of doing an STA sign-off, engineers will use the dot lib to do the STA, and once all the timing results are clean, they go for the tapeout. After the silicon comes back, surprisingly some of the chips start failing even after fixing all the timing violations, and it is happening especially when the industry started moving towards the advanced technologies. Then the people started thinking about what is the reason for the failure and what is the root cause. After a lot of study, it has been came out that there are some unexpected changes are happening in the manufacturing process which are causing the change in the transistor behavior, which in turn resulting into the failure of the chips. These changes are referred to as variations. At the advanced technologies, variations are becoming a very common or predominant cause for the failure of the chips if they are not taken care properly in the design closure. Here, when we are talking about variations, many of them are unseen and unpredictable by the engineers who are really working on the chips and doing the sign off. The variations are mainly classified into two categories. One is the process variations and another one is the environmental variations. The process variations are mainly caused because of the manufacturing process itself, where the P&R engineer do not have any control. The process variations are further divided into local variations and global variations. Just to take an example of the same AND gate which is placed at two different locations on the same die will behave differently with respect to the propagation delay, and the variation which are causing this effect is called as a local variations. The same kind of issue will be seen with even more delay difference when we are trying to compare two AND gates which are placed on two dies which are from the same wafer or from the different wafers or from the different lots. This kind of scenario is called as a global variations changes. On the other hand, there is another classification called as environmental variations, which include the change in the temperature and voltage combination at which the combinational gates is working. Global variations are modeled by the foundry in the form of a process corner, and these process corners will be taken care in the design through the timing libraries which are characterized at different process conditions. This will be taken care with the provided library conditions and closing the timing at all these particular corners. Global variations can be captured well by running the static timing analysis at multiple PVT corners. When we come to local variations, these cannot be handled with the traditional corner based timing methodologies, and all the local variations need to be modeled by using different methods depending on the technology at which we are working on. Some of these particular techniques are OCV, AOCV, POCV, and the latest one is LVF. The end goal for this particular exercise is just to make sure that the chip which is being manufactured will work reliably even after having the several variations in the manufacturing process. The first source of variation we are going to talk about is the voltage variation. In general, the propagation delay of any standard cell depends on the supply voltage. That is, increase in the voltage speeds up the transistor and decrease in the voltage slow down the transistor. The operating voltage for which the chip is going to be decided by architecture requirements such as frequency of the design at which it needs to be operated and what is the overall power requirements. For example, if you take a 0.8 volts as the operating voltage, ideally it is expected that all the instances in the design should get the same supply voltage, but in reality the transistors will not get a 0.8 volts because of several reasons. The major reasons for voltage variations are: the first one, accuracy of the voltage regulator itself. That means it might not provide the exactly expected supply voltage, but it is plus or minus certain percentage of the required supply voltage. This means at the source of the voltage supply itself, the variation is getting introduced. Second one, the general supply network is built by using a metal layers. So by default it becomes as a non-zero resistance network. The resistance in the network will be less to the cells which are placed nearer to the source and more for the cells which are placed away from the source. This means that the supply voltage for the cells mainly depends on the voltage drop across the various regions of the chip. Because of this reduction in the supply voltage, the propagation delay of the cells is going to be increased, and the same need to be taken care when we are doing the sign of timing analysis. If you take that picture which is shown on the top left side, because of the same resistance requirements at different stages, there is a continuous drop and which is causing the cells to have a less voltage compared to what is really required. Third one, because of the noise which is getting introduced into the power supply network, the voltage can be varied. The last one, based on the functionality requirements, the same instance can be operating with the different activity factors at different instances of time, which has a direct impact on the voltage requirements. By keeping all these particular things as a context, if you want to make sure that the chip has to work even after these voltage variations, we need to make sure that the design need to be closed at different voltage conditions rather than only one, that is 0.8 volts. Because of this reason, we are going to do the timing closure not only at 0.8 volts but also at plus or minus 10% of the typical voltage. That means we are going to do the timing closure between 0.72 volts to 0.88 volts. So as a summary, the performance of the transistor really depends on the voltage, and all the voltage variations has to be taken care into account whenever we are doing the design timing closure. The second source of variation we are going to talk about is a temperature variation. Once again, in general, the default behavior of the transistor is that the delay will change with the change in the temperature. There are two kinds of temperatures we need to be talking about which will impact the performance of the design. One is the ambient temperature, which is a normal room temperature at which the transistors are being operated. Another one is a junction temperature, which is the sum of the ambient temperature and the temperature increased due to the power dissipation of the circuit on the chip itself. Ambient temperature depends on the application of the chip. For example, if the design is targeted for a general commercial purpose such as a TV, then the temperature range might be 0 degrees to 70 degrees. Or if it is an industrial standard application, the temperature might be minus 40 to 85 degrees. Else if it is a military related application, then the range even gets increased, minus 55 degrees to 125 degrees. Since the junction temperature will be obviously more than the ambient temperature, we need to target for a more wide range than the one which is shown in the table. For example, for a commercial applications, the normal range is 0 degrees to 75 degrees, but after considering the junction temperature, it will be minus 40 degrees to 125 degrees centigrade. So as a summary, the delay of the transistor will change with the change in the temperature. So whenever we are doing the timing closure, we have to do the timing closure at extreme corners of the temperature and as well as at the intermediate points. The third source of variation is the process variation, is also referred as a manufacturing variation, which mainly occurs when the ICs are getting fabricated. The process variations will have a direct impact on the characteristics of both transistors as well as the metal layers. The main source of process variations are random dopant fluctuations, oxide thickness variations, and line edge misalignments. Any or some of these leads to a variation in the mobility or threshold voltage and subsequently the IDSAT currents, which impacts the performance parameters such as delay and power of the device. Since the manufacturing of the IC involves many steps such as lithography, etching and diffusion etc., and when we are moving towards advanced nodes, these are happening at an atomic level. So controlling of these parameters for not to have variations is very difficult. As discussed previously, the process variations are majorly divided into global variations and local variations. We will talk about these in detail in the next slides. There are certain key parameters of a transistor such as channel length, oxide thickness, and for metal layers it's metal thickness and metal width. In the process of manufacturing, because of the variations in the process itself, any of these physical parameters can have a direct impact. This particular impact will in turn change some of the electrical parameters of a transistors and metal layers. Because of this change in the electrical parameters, there will be a change in the design parameters such as performance and power. Just to take an example, whenever there is a change in the doping concentration, it will have a direct impact on the mobility of the electrons, which will impact drain current, and whenever there is a change in the drain current, obviously it will have an impact on the performance of the transistor. In the another example, whenever there is a change in the oxide thickness, it will have an impact on both performance and power. So as a summary, the variation in the physical parameters will lead to the change in the electrical parameters, which in turn will affect the transistor performance and power. Now we are going to talk a little bit more in detail about the global process variations. The variations which are caused between the lot to lot, wafer to wafer, die to die are called as a global process variations. When we compare the impact of global versus local process variations, impact of the global variations on the delay is higher than the local variations. Because of this delay changes, some of the chips become slower and some of the chips become faster. If you take any transistor, the process corners are classified as 5 different types, and the same is shown in the slide. TT, which is nominal, SS slow and slow P, FF fast and fast P, and similarly SF and FS. In general, the foundry provides the models for SSG, TT, FFG, and these models are used to generate the different timing libraries which are used by the implementation engineers or by the STA tools to do the timing analysis. Let's bring environmental variations also into the picture at this point of time in continuation with global process variations, as both of these are handled in more or less same way. Both global process variations and environmental variations collectively will have an impact on the speed of the transistors. Just to take an example of temperature, depending on the ambient and junction temperature, the chip can have a temperature range from 25 degrees to 85 degrees. But it will be difficult to do the timing sign off at each and every value of the temperature. Similarly, the same case exists for the voltage also. So as a solution for every technology, depending on the application, a set of PVT corners are chosen to do a design sign off by considering the global process variations and environmental variations. Closing the design sign off at these particular PVT corners will guarantee the performance of the design under the different process and environmental conditions. To give a summary on the global variations, the performance of the transistor will change with the voltage change and the temperature change. So, and also because of the global variations, some of the chips will become faster and some of the chips will become slower. To consider all these particular global and environmental variations, we are going to consider the different PVT conditions for doing the timing sign off. Global process variations will also have an impact on the chip interconnects as well as the via structures apart from the transistor performance. Because of global process variations, the thickness and width of the interconnects will change, which will have a direct impact on the resistance and capacitance of the metal layers. Based on this context, there are different types of models are evolved which need to be considered when doing the RC extraction of the nets in the design. Some of these examples are typical, C-best, C-worst, RC-best, RC-worst. Just to take an example of a generic application which will work with a voltage of 0.8 volts plus or minus 10% and with a temperature range of minus 40 to 125 degrees and with a different combination of RC models. With all these permutations and combinations, we are getting almost 16 different combination of the runs need to be done to make sure that all the global variations are considered and there are no issues with respect to timing. And in the latest SOCs, DFT is one of the must feature, and when you start introducing the DFT, there is an extra modes are coming into the picture apart from the functional mode. So if you combine both DFT modes and functional modes, there might be approximately 4 to 5 different modes is going to be there for doing a timing sign off. So when you try to combine both modes as well as the corners, so if you take a 5 different modes and 16 different corners, there is almost like 80 timing sign off runs need to be done. So whenever we are moving towards the lower technologies, whenever these particular process corners are getting increased for doing a timing sign off, then the overall runs need to do a timing sign off will drastically gets increases. Since it will be very difficult to do the implementation of all these particular scenarios, engineers will choose some of the dominant corners for implementation and do the timing sign off in all the corners to reduce the overall run times of the chip. Till now we have spoken about global variations where the same logic gate differences are seen across the dies. But now we are going to talk about change in the behavior of the logic gates which are placed in the same die at different locations. Local variations are mainly divided into two types. One is random local variations and the second one is systematic local variations. Random local variations are mainly due to parameters which need to be controlled at atomic level. So it's very bit difficult to control these particular violations. Foundry provides certain Gaussian distribution parameters which need to be somehow modeled into our design closing methodologies. So we are going to talk about all these particular methodologies a little bit more in detail in the next slides. Systematic local variations are less impact compared to the random local variations. One of such example is location or distance based. When two instances are of the same logic gate placed at closer distance, that will have a less impact on the behavior compared to the when these particular instances are placed at a longer distance. We have spoken about the local variations and understood that local variations will have impact on the delay of the cells which need to be accounted when we are doing the timing closure. Take an example of a buffer which is connected back to back for 4 times. So the depth of the path from A to B is 4. If the mean delay of the cell is assumed as 50 ps, then the overall delay from A to B is 200 ps without consideration of any of the local variations. If you assume 1 sigma delay change is 2 ps, then with 3 sigma the delay range will be from 44 ps to 56 ps. That is nothing but 50 ps plus or minus 6 ps. So by considering the 3 sigma variation, if you calculate the delay from A to B with a worst case assumption, then the delay will be anywhere between 176 ps to 224 ps. That is almost like 48 ps. In the lower nodes, this is very significant. But in reality, since all the cells will not really go to the extreme conditions, and also because of the cancellation of the random variations across the cells, whenever the depth of the logic is more, we should remove certain pessimism which is involved in the above said calculations. There are several methods which are evolved over the period of time which we will discuss in more detail in the next slides. One of such technique is shown here where the statistical addition is done which resulted in an overall delay from A to B as a 212 ps. Because of this we are getting a benefit of 12 ps. So as a summary, with increase in the logic depth, random variations will cancel across the cells and percentage of the variation reduces. As said before, there are several methods evolved over the period of time. You can see the same in the slide. In the older technologies, that is 180 nanometer and above, a fixed margin is used as uncertainty for the design timing closure, which is very pessimistic, which results in unnecessary increase in the area overhead, and also it's very difficult to fix all the timing violations. To reduce the pessimism, other methodologies are evolved which are known as OCV, AOCV, POCV, and the latest one is LVF. We will talk about these in depth in the next slides. But as a common in almost all the cases, general criteria used is for setup analysis, the launch clock path and the data path delay is increased and the capture clock path delay is reduced. And for hold, it is vice versa, where the setup and hold checks are done in a more worse situation compared to the normal timing analysis. OCV is referred as on-chip variations. In this methodology, the delay change for the cells is considered in terms of a percentage of D rate, and this D rate is same for all the cells in the design irrespective of the logic depth. As shown in the picture, for setup analysis, for all the cells in the launch clock path and combinational path, the delay for each cell is increased by 6%, and for all the cells in the capture path, the delay is reduced by 5%. OCV can be applied with a different percentage of D rates. If you consider the worst case OCV D rate, then obviously it will cover all the paths in the design, but this is very pessimistic. In the other scenario, if you consider the less percentage of the D rate than the worst case, which will cover all the long logic paths, but for the shorter paths, we will get optimistic results which might impact the yield, because of which there might be some timing violations on the real silicon. So as a summary, in OCV, a single D rate will be used for all the cells in the design, and because of which all the shorter paths will become as optimistic and all the longer paths will become as a pessimistic, because of which there is a direct impact on the area and power of the design. AOCV means advanced on-chip variations. To overcome the drawbacks which we have seen in OCV methodology, AOCV came into the picture. Unlike a fixed value of D rate in OCV, in AOCV there will be a different D rate for the same cell based on the depth. Here the depth means logic depth from the starting register. All the cells in the library will have these new AOCV D rates added for different depths. For the same cell, when the depth is less, the D rate is more, and when the depth is more, the D rate value will be less. Just to take an example as shown in the slide, for a buff X4, for depth 2 the D rate is 8.7% and whereas it is 2.7% for the depth of 20. Because of this methodology, accuracy for the shorter paths improves and pessimism for the longer paths reduces. Some of the foundries will also support distance based D rates which are mainly to take care of the systematic local variations. That is less D rates for the two cells which are placed next to each other compared to the one which are placed away from each other. So as a summary, in AOCV the different D rate value will be applied for different cells based on the depth, and it really reduces the optimism or pessimism which is involved in OCV. In general, there are two ways of doing timing analysis. One is graph based and another one is a path based. By default, all the timing engines are graph based timing analysis tools. We will discuss a little bit more in depth of how the GBA based timing analysis is done by using a AOCV tables. Just to take an example, there are three different logic depth paths shown in the picture. We will consider two among these particular paths for our analysis. Path 1, flip flop 1 to flip flop 3 with a logic depth of 15, and path 2, FF2 to FF3 with a logic depth of 5. When the tool do analysis for the FF1 to FF3, since the logic depth is 15, a D rate value corresponding to logic depth is assigned to all the cells in the combinational path. On the next step, in continuation to the timing analysis, when the tool do the timing analysis between the paths FF2 to FF3 in which the logic depth is 5, all the cells should get a D rate value corresponding to 5. But if you see in the picture, there are cells from U4 to U7 which are overlapping between the path 1 analysis and path 2 analysis. In this kind of scenarios, the expectation is that the tool should only consider a D rate corresponding to depth 15 for the path 1 analysis, but unfortunately it used a D rate value corresponding to depth 5, which is pessimistic. Because of this, almost there is an extra 5.63 ps of delay is being added for the path. So as a summary, logic depth D rate is assigned to each cell depending on the shortest path that goes through that particular cell, which adds a pessimism to other paths through that particular cell. POCV means parametric on-chip variations. This methodology is introduced to avoid the drawbacks seen in the AOCV methodology. In this methodology, instead of different D rates for different depth paths, each cell will be having a single POCV coefficient value. When POCV came into the picture, the normal STA engines are not sufficient to do the timing analysis, and for the same, new engines are evolved which are called as a SSTA. POCV uses statistical approach, but it doesn't do a full SSTA analysis. Instead, it calculates the delay variation by modeling the intrinsic cell delay and load parasitics to determine both the mean and sigma of the logic gates. If you take the same example where 4 buffers are connected back to back with each other and the path delay is from A to B, with a certain assumptions that the cell delay is 50 ps and sigma is 2 ps, then the overall path delay from A to B is addition of 4 buffer delays, which is nothing but a 200 ps, and the arrival sigma value will be 4 ps with the equation which is shown in the slide. If you want to consider the overall path delay with 1 sigma variation, that will be 204 ps, which is nothing but a 200 ps plus 4 ps. And if you want to consider the overall path delay by using a 2 sigma value, which is 208 ps, and for 3 sigma it's 212 ps. So whatever the sigma value which is chosen for that particular technology and for that particular foundry guidelines, we are going to take that particular value, and that particular value is going to be used for the timing sign off. As a mean and the sigma are propagated through the path, accuracy of the path delay variation does not really depend on the logic depth. As depth is not assigned to a cell, it overcomes the graph based pessimism which is involved in AOCV. The improvement which we can see in this particular methodology is the coefficient is calculated based on the single transition and the load for a particular cell, whereas in reality it is not the case. So as a summary, in POCV it reduces the pessimism which is involved in the GBA based AOCV analysis. LVF means Liberty Variation Format. Unlike the POCV, where the coefficient is calculated for a single input transition and output load, in LVF methodology, the variation is modeled for a different slew and load values. For example, if you look at the table, it is a 2 by 2 matrix of D rates for different input transitions and output loads. This is pretty much similar to a delay table. This is more accurate and close to the SPICE simulations. So this is one of the latest techniques what industry is following at this point of time to consider the local variations. We have generated a couple of comparison results between the AOCV timing analysis and POCV timing analysis for the same design, and the chart shows the total number of violations for setup and hold are pretty much less compared to AOCV methodology, because of which the total number of hold buffers which are going to be added for the design are less, which in turn benefits with respect to area and power. And also we have took couple of timing paths, and the same timing paths are done analysis with respect to AOCV methodology, POCV and LVF, and also with respect to SPICE. So when you look at the results, the LVF results are more towards closer to the SPICE analysis compared to POCV and AOCV, and when you compare between POCV AOCV, POCV results are better. So as an overall summary, we are seeing a little bit more results with LVF compared to POCV and AOCV, which is the latest methodology people are adapting at this point of time. As an overall summary, the process variations are divided into global and local, and all the global variations are considered by using a PVT coordinates. Local variations are modeled by using any one of the discussed methodologies. Just to give a summary of all the methodologies we have seen, OCV is a fixed D rate which is pessimistic for longer paths and optimistic for shorter paths. AOCV is introduced to take care of OCV pessimism or optimism, in which the STA tools will also consider the depth of the path as an extra input, and D rate is applied on the depth based. But AOCV GBA analysis is pessimistic, and the D rate which is used is generated for a single load and single slew value. POCV is introduced to reduce the pessimism in GBA mode, where a single coefficient value is used for each cell. Once again, here also the coefficient is generated for only one slew and load values. To improve the accuracy, LVF methodology has started, in which the D rate value is modeled based on the actual load and slew values for a particular cell.
Hello everyone, hope this webinar has been fruitful to all of you. So we will wait for a moment, and I request all of you to proceed with your questions which you have for Srikanth. You can put that in live chat, and our moderation team will look at it. And
Hey, let's have a question and answer session. So there is a question from Sudhir. So can you show it to me? So what is the kind of variations will be covered as part of the distance based AOCV and depth based AOCV? In the distance based AOCV, the systematic variations are being considered, and in the depth based AOCV, the local variations are mainly considered. That's mainly on the particular thing. And the next one is there is a question from Yogesh. It's mainly on the aging factors. Yes, we do consider the aging factors whenever we are doing the timing sign off analysis. Aging factors are in general provided by the foundry, where they will say that like there's a particular amount of derating factor which need to be used for a particular amount of number of years if it is really required. So those particular aging factors we are going to consider along with the normal other variations which are being considered as a AOCV and all those things. So yes, we do consider the aging factors whenever we are doing the timing analysis, and these are being provided by the foundry. Okay. There is a question from Sitaram. So the question is like, is there any extension for the LVF format? It's not exactly there is a methodology change, but there is an extension for the LVF format, the current LVF format really considers only the sigma variations in a single table format kind of thing. But when we are moving towards the lower technologies, less than the 0.5 volts kind of thing, the delta between the threshold voltage and the real voltage is being very less, and which is really causing us a couple of other variations. To take care of those particular variations, there is another new format of the LVF came into the picture, where apart from the normal sigma table, other more tables are being used in the library, which will really provide a more accuracy for the timing analysis, which is called as a moments based LVF basically. So other question we have. So you want to show something? So there is a question from Rama, which says that can you elaborate on the logic depth in the AOCV? The logic depth is nothing but it's a logic levels from the starting of the register at what level that particular combination cell is being placed. That's nothing but we used to call as the depth of the logic level basically. So if there is a path from register to another register of total logic levels 50, so a cell which is being placed at a logic level of 4 or 5 is called as at a depth of logic level 4. So we can being posted, like please make sure that you comment them in the comment section in the INVECAS YouTube channel. We will try to provide the answers for as many as possible as quickly as possible. Thanks for everybody.
Webinar has been fruitful to all of you, and it has given you very much depth insight on design timing closure considering process variation. We will come up with the next chapter and next interesting topic for you guys. Just keep posting what you want to listen at INVECAS YouTube channel, and good day to all of you, and keep subscribe our YouTube channel, like, share all the videos, whatever you like, and any questions which you have forget to mention or which you can recall later on, put it on the comment section and we will try to answer that as soon as possible. Have a good day ahead. Thanks to all.